Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In this video, we mentioned some methods are there, right? So in that, we will see unit load method. In previous video, we have proved that how the Maxwell reciprocal theorems, we derived that Maxwell reciprocal theorem. In that, what we had seen, the deflection at point 1 because of point load acting at point 2 means this one was there. So this topic we will cover in this load. First, we will see the principle of a stationary value of the total complementary energy, then application to deflection problem, and then unit load method. So in previous video, what we have seen that we have proved what reciprocal Maxwell theorem. In that we had seen some arbitrary shape is there, and there at point 1 load P1 is acting, at point 2 P2 load is acting. So then what we have? We found the deflection at this point because of this load. Right. So according to Maxwell law, deflection at this point because of this load will be equals to deflection at this point because of this load. Right. That was the Maxwell reciprocal theorem, and that we proved that also the derivation. For first we had seen for n number of loads, and then finally just we reduced to 2 loads, and then we proved what A12 equals to A21, that flexibility constant, and hence that we can say that Maxwell reciprocal means the energy is stored in both at point 1 because of 2 will be equals to that energy stored at point 2 because of load 1. Okay, now come to this video. So first we will see about the principle of a stationary value of the total and complementary energy. Then we will go for the application to the deflection problem, and then we will see by unit load method how to solve the problems. Okay, so first, the principle of a stationary value of the total, the value of the total complementary energy. Let's see here. Total complementary energy. Okay, actually that comes down. The principle of a stationary value of the total complementary energy may be stated as. So what is the definition, or what is that? For an elastic body in equilibrium under the action of applied forces, the true internal forces or stress and reaction are those for which the total complementary energy has a stationary value. So once again, for an elastic body in equilibrium, so when is that body is in equilibrium under the action of applied force. So when a force is applied on the body, elastic body, and that body is in equilibrium, right? The true internal forces because of which that body is in equilibrium, because we are applying the force. Suppose this is there, right? After applying the forces, what happens? This will move, but still that body is in equilibrium. Then what happens? Definitely some internal force is acting opposite to the applied force. That is equal, and that's why that this body is in equilibrium. If this force will be more, then body will move, right? So this internal is lesser than the external what we are applying. So in that case, for equilibrium, externally what we are applying, that must be equals to the internal force also. So true internal forces or stress and reactions are those for which the total complementary energy has a stationary value. Means that will be for a complementary energy should have a fixed or a stationary value. Means that complementary energy value should not change. Okay, so let's see how. Consider an elastic system in equilibrium supporting forces P1, P2, P3, so on, which produces real corresponding displacement. Here it's a delta 1, delta 2, delta 3, so on, delta n. So real displacement at because of point 1, that at point 1 delta 1, at point 2 delta 2, at point 3 delta 3, so on at point n delta n. This is the displacement. If we impose virtual forces delta P1, delta P2, so on, delta Pn on the system acting through the real displacement, then the total virtual work done by the system. Now what we are doing? We are applying or imposing a virtual forces delta P1, delta P2 and so on that particular point, whatever is there, like delta P1 at 1, delta P2 at 2, so on, delta Pn at point n. Now because of that virtual load, what will be the through real displacement? Then the total virtual work done by the system. So total virtual work done we are finding. Will you got the first complementary energy that will be stored, that is entire the volume. So that's why it's negative, and this R equals to 1 to n for the all because total R forces. So deflection into load, that will be only the work done. So delta PR stands for what? R equals to 1. If 1 is there, then delta 1 into dou P1 plus delta 2 into dou P2 plus delta 3 into dou P3, so on delta and dou Pn. So instead of writing so long, what we are doing? We are writing in this form. Means whatever the number is there, suppose 4 numbers are there. So this we can write R equals to 1 to 4 delta R into dou PR. So let's see how we will write for this one. So first put R equals to 1 wherever is there. So delta 1 dou P1. This symbol is for sigma, summation. So plus, now put R equals to 2. So up to 4 we have to go. So delta 2 into dou P2 plus delta 3 into dou delta 3 into dou P3 plus delta 4 into dou P4. So up to 4 is there. So these 4 terms are there. So instead of writing this 4 term is okay, somewhat it's shorter, but many numbers are there, then what we will do? So here we have taken that n number. So instead of writing up to n, simply in short, we can write this one. Okay. So now, the first term in the above expression is the negative virtual work done by the particle in the elastic body. So negative virtual work done by what? By the particles in the elastic body. So whatever the particle inside that is there, that is doing the virtual work to keep it in equilibrium. So we are applying this force, and internal particle whatever is applying, that definitely will be opposite to that one. So that's why this first term is the internal particle, because of which this one is in equilibrium. So even after applying the load, so after applying the load is this term. Okay, and to resist this one or to keep this is in equilibrium, whatever the internal force is acting, that is this one. Okay. So this is work done because of the external force, and this is work done because of the internal force, because of which the body is in equilibrium. While the second term represents the virtual work done of the externally applied virtual forces. So we are applying delta P1, delta P2, so on virtual force. So this is virtual work done externally, this is internally. Okay. Now from the principle of virtual work, what? That sum total should be equals to 0. So just make it that equals to 0. So from here what you can say, negative of integral, this volume stands for this integral of entire volume, or you can say simply 0 to whatever the shape is there of that volume. Suppose a sphere is there, for that sphere you are finding, then it will be 4 by 3 pi r cube. So instead of writing, simply you can write here volume, area, length. Length means entire length. Once you will write this one, means no need to consider that half, 1/4 or what. That will be for the total. So 0 to means from the starting to till ending of the volume, till ending of the area, length, whatever you are taking. Right. So now take this term this side. So from here what you will get? This one, integral of volume y dp equals to sigma r equals to 1 delta r into dou pr. Okay. Now instead of writing this one, right, this is in the bigger form, just writing in the smaller form. Right. So for this here the Ci is volume 0 to p y dp. So that's why here delta term is there. Right. Delta of Ci, because delta and integral will get cancelled. Once we will integral, we will differentiate, then this will get cancelled. So that's why, because here only one integral is there. So here delta term is taking common, means one more integral 0 to p y dp, and C is this term. C is what? Minus of r equals to 1 to n delta r pr. So because in terms of positive we are writing. So if here taking negative common, right? So just making this term as positive. So this will be negative. So Ci taken positive, so this is negative. So now instead of writing this, we can write in short delta, this is not mod, this is just one, delta of Ci plus C equals to 0. What is Ci here? Ci is first integral volume into, and then that is double integral 0 to p y dp, and that second integral is the volume, and C is the sigma of r equals to 1 to n delta r pr. We shall now call the quantity Ci plus C, this term is the total complementary energy C of the system. So that's why that is the principle of a stationary value, that right. So now here that Ci plus C will give the total complementary energy of the system. Okay. So now application to deflection problem, how we can apply this one. So just here this concept we will use here, right? And that only. So how to use that one? So just here. Let us suppose that we require to find the deflection delta 2 of the load P2 in the simple pin joint framework consisting, say, of K member. So in a joint, any means they are having K member, means 5, 10. That K will be 5, 10, 20, anything, depending upon how many members are there, right? So for K member, we are finding. And supporting loads P1, P2, P3, so on, Pm. As shown in figure, that we are seeing that figure, right? For that same figure we are, sorry, here not there, for the same previous figure that we are, okay? From the above equation, the total complementary energy of the framework is given by C equals to sigma of I equals to K 0 to Fi, from where to where, right? Lambda I dFi. So here dFi will change according to the member, where I is what? For first member 0 to F1, that only load gradually we can apply, lambda 1 dF1 minus here R equals to 1 to 1, so delta 1 to n. So delta R PR, so delta 1 P1. Similarly R equals to 2, delta 2 P2, right? And this stands for the first member. So this is the total virtual work that inside, and this is because of the external one. So here where lambda I is the extension of the ith member, right? Means this is the elongation, lambda equals to that deflection equals to PL upon AE, right? Have you seen this formula before? Delta or deflection equals to PL upon AE, right? That is only here deflection. So instead of delta they use just lambda. So lambda I equals to PI-LI by AI-EI. Now put the value of A. For first member I will be 1, for second member I will be 2. So for lambda 1, P1 L1 by A1 E1, right? So that is the general formula. If suppose same material is there, then what happen? E will be same. If having the same cross section, then same cross section, then A will be same. Same material, then E will be same. Then we can keep constant, only this will change. Okay. So yeah. So Fi is the force in the ith member. Means first you have to find force in that particular member. So in each member you have to find the force. Okay. And R the corresponding displacement of the rth load PR. So just again simply PR is the rth load. Now depending upon how many loads are there. For second 2 loads, 2. Here how many loads are there? 2. P1 and P2. So this will be K 2 members. So K I equals to 1 to 2. And if 2 numbers are there, then also R equals to 1 to n. Right? So that depends on the how many total members are there in that structure. Okay. So from the principle of a stationary value of the total complementary energy, this delta C by del P2 means differentiate that just with respect to del P2 for second one. Right? So here this will be I equals to 1 to K lambda I del Fi by del P2 minus delta 2, or just see here this equation. Okay. So I'm taking for the second one because at point 2 we are finding, so load P2. So this will be C equals to, I'm writing just sigma I equals to 1 to K 0 to Fi lambda I dFi, right, minus, right, now just I'm removing this one, minus delta 2 P2. Now earlier also I said that at what point you are finding, differentiate with respect to that one. So at point 2 finding means differentiate with respect to P2. So delta C by del P2, right, equals to this also will get differentiated. So sigma I equals to 1 to K 0 to Fi lambda I dFi by dou P2, and here differentiation of P2 will be 1, so minus delta 2. And from the again conservation of principle of energy, this must be equals to 0. So from here lambda 2 equals to what? This term. Right. So here delta 2 just differentiated with respect to P2. So now from this delta 2 equals to what? This term. I equals to 1 to K lambda I delta F I by delta P2, that is delta 2. Equation is seen to be identical to the principle of virtual force, in which virtual force delta F and delta P acts through real displacement lambda. So this already this similar equation we had seen, right? So delta 2 equals to I equals to 1. Now here we have to find that lambda. Just now I told you that equation, and later also we will see that one. So lambda 2 equals to I equals to 1 to k lambda I dou fi by dou p2. This will be the deflection. So now what we have to do? First find lambda I, means lambda 1, lambda 2, lambda 3, so on. Then because of that force with respect to p2, what will be there? So find force in each member and then differentiate that with respect to the load at what point you are finding. If suppose at point 2 you are finding, then p2, at point, then delta 2. If at point 1 you are finding, then lambda 1 will be, delta 1 will be equals to, at point 1, so delta 1 equals to sigma 1 equals to, I equals to 1 to k lambda I dou fi by dou p1. Just that will be the difference. Means at what point you are finding, differentiate with that load, whatever is acting at that point. So here at point 2, P2 is acting, so del P2, the virtual force, that del P2 is virtual force that we are applying. Okay, so just differentiate with this one. Okay, so now let's see here that for linear elasticity, that lambda I equals to Fi Li by Ai. I just told you lambda equals to Fl upon Ae. Right. So for first member, if same member is there, then A and E will be same. If different material and different cross section will be there, then it will be different. So this is the general one. And Fi, put lambda 1 means F1 L1 by A1 E1, lambda 2 F2 L2 by A2 E2, so on, depending upon how many members are there. So like that, we have to first find lambda. Right. If same material and same cross section is there, then no need to find, then simply we can write 1 by A E and common sigma Fi Li. That will be the lambda. Okay. So AE we can just take common out and this will be the total lambda. Okay, or simply lambda 1 is 1 by AE into F1 L1. If suppose length is also same, for each member length is same, but that is not necessary that length will be same, cross section may be same, right? They may give depending upon the equation. So then if length is also same, then same thing becomes lambda 1 equals to L by AE into simply F1, right? Lambda 1. Lambda 2 will be L by AE into F2, like that. Okay. Where Li, AI and EI are the length. So Li is length, AI is the cross section area, and EI is the modulus of elasticity, or in another word that is also called as Young's modulus of elasticity of the ith member. So that particular member, whatever is there for first member, modulus of elasticity of first member. On the other hand, if the load displacement relationship is of a non-linear form, so this is for what? Linear form, non-linear form. So already we derived in previous video for the non-linear. What happened? Fi equals to B lambda I. See, their deflection was Y, so in terms of P B power Y, that there we have taken F equals to, or P equals to By to the power M. There we consider P as the load and Y as the deflection. Here we are considering F as the force and lambda as the deflection. So same just the equation. P equals to B Y to the power N. Here N is C. This again the constant here, in which B and C are known, that constant, and delta 2 equation becomes. Now just shift here. So what we have delta 2 equation here, right? So here just replace this lambda I value or Fi. So from here what we will get? Lambda I will be equals to, so just see, Fi equals to B into lambda I power C. So Fi by B equals to lambda I power C. So from here lambda I equals to Fi by B power 1 by C. So just change here. So this is the value of lambda I into dou Fi by dou P2 here. So just lambda I into dou Fi by dou P2. So this is lambda value. Right. Now depending upon whatever the value is there, just put that one, we will get the deflection. Okay. So now just see This is very important. This point you have to remember before solving the question. If you won't get, then it's very difficult to solve the numericals. So these points are very important. All the points is very important, and that make sure to remember all the points. Okay, so that's why it's remember here point to remember. So again, this system is there. So just see how many members are there, because we are seen for n members. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? So total 11 members are there, means I equals to 1 to 11. Right? Now just see here. Like suppose this is a point 1, because load is acting point 1, point 2, point 3, right? Point 4, point 5, and so on. So this is point, and like that it is there. So loads are acting. It's not necessary for all the points load will act. In some question they will give only at this point, or this point, means any number of load, but the structure will be same. But at any 1 point, 2 point, 3 point only, load will be there. And then they will ask to find the deflection at some certain points. So just here. We note that the support reaction do not appear in equation, right? Support reaction, this one. This convenient absence derived from the fact that the displacement delta 1, delta 2, so on, delta n are the real displacement of the frame. So whatever is there, that is the real. So now we are applying the complementary energy. The complementary energy of a reaction at A and the vertical reaction at B is therefore 0. So at this point and at this point, the vertical reaction will be what? 0, since both of their corresponding displacements are 0, because here there is no displacement of this point, right? No displacement means their reaction will be 0. If we examine equation A, we note that lambda I, just we are seeing that equation A here, right? So just here, lambda I into dou Fi by dou P2. So equation A, we note that lambda is the extension of the ith member. So for first member, lambda 1, lambda 2, lambda 3, so on. A are those corresponding to the load P1, P2, Pn, so on. So lambda 1 for P1, lambda 2 for P2, lambda 3 for P3, so on. The term dou Fi by dou P2 in equation A represents the rate of change of Fi with P2. So see here. Remember, rate of change of Fi, how Fi is changing with P2. Okay. So rate of change of Fi with P2 and is calculated by applying the load P2 to the unloaded frame. Remember, P2 to the unloaded frame means whatever load is there, just remove that one and apply only the load P2, determining the corresponding member load in terms of P2. So now determine the corresponding loads in all the member in terms of P2. Why? Because now after removing all the loads, only the P2 load is acting. Meaning what here, at whatever the point you wanna find, remove all the loads and apply one fixed load. That next time we will see, apply the fixed load at that point only and then calculate in terms of that fixed load. Okay, so that is here. This procedure indicates a method for obtaining the displacement of either a point on the frame in a direction not coincident with the line of action of a load. So let's see once again. This procedure indicates a method for obtaining the displacement of either a point on the frame in a direction not coincident with the line of action of a load. So means what? It's not necessary the direction of incidence is in the same, it's in the direction of line. In fact, a point such as C which carries no load at all. Means what? At point C there is no load. So at this point also deflection will be there. It's not necessary load is acting here, so only displacement will be here. Load is acting here means only displacement will be in this direction. No. Wherever load is not acting, there also displacement will be there, because already we had seen what? Because of at point 1 because of load, point 2. So at point C because of these loads also the deflection at point C will be there. Okay. We place at a point and in the required direction a fixed or dummy load, say PF, right? So see, we place the point at point and in the required direction means let's apply a fixed load at which point you want to find the deflection, because that only P2 at point 2 P2 was there. So here there is no load, means you have to apply the fixed load at that point where load is not given. If load is given like at this point, then no need to apply. Here it's not there, and if you want to find deflection here, then you have to apply the fixed load here. So that you have to remember at which point you are finding. Just check whether load is given or not. If load is given, then no need to apply. Directly you can find. If load is not given, then apply a fixed load at that point, because then only we can apply the energy principle. Right? There also load should be there. Means load at point 1 because of point 2 and because of point 1 also. So at that point load must be there. So original load being removed. Now remove all original load, only the virtual load that is acting, that as PF. Okay. Substituting in equation A, produce the required deflection. Now substitute in equation A. What is equation A? Here. Put that one. Right? Sorry. It must be pointed out that it is not absolutely necessary to remove actual load during application of PF. One more thing. It's not necessary, that's why I told you, if load is there, then at that point you are only finding, then no need to remove the other forces. With that force only you have to find, and no need to add the fixed force. If at that point load is not there, then only you have to add. So by both the method you can solve depending upon at what point you have to find the deflection. The force in each member would then be calculated in terms of the actual loading and PF. Right? Now the force in each member first find, and then next with respect in terms of PF also, means when actual load is acting in terms of that one, and when PF applied, then what will be the load in each member. Fi follows by substituting PF equals to 0. Now Fi, just put wherever the, because PF we have taken that fixed load, so put that value as 0. So PF equals to 0, and dFi by del Fi by del PF is found by differentiation with respect to PF. Now whatever the force is there, because we have to remove that force, right? So make PF term as 0 and differentiate that, like suppose that delta P2 we found, delta 2 we found, then what we did with P2 we differentiated. So here fixed load, suppose at this point you are finding deflection at C, so whatever fixed load you applied, suppose here fixed load you applied PCF, sorry, PCF, then differentiate with respect to del PCF, or differentiate with respect to PCF. So whatever load is acting at that point, with respect to that you have to differentiate. Okay. Obviously the two approaches yield the same expression for Fi and del Fi by del PF, although the latter is arithmetically clumsier, but this one is somewhat difficult, that we will see how to that one. Okay. Now come to the unit load method, is how to find by unit load method. So here we will see only the derivation. Later we will see the numerical also, and same numerical but with numerical value we will see. Similar data structure will be there, and we will see the numerical value. So first, how to solve the unit by unit load method. The method for a linearly elastic structure can be simplified as follows. How? Consider the framework in figure. So this is the framework where we need to find the vertical deflection at point C. So just see, at this point we are finding. So here what is there? Load is not there. Right, at this point load is not there. Means what we have to do? We have to apply a vertical fixed load or dummy load PF. Okay. Following the procedure, we would place a vertical dummy load PF. So see, a vertical dummy load PF at C and calculate the framework total complementary energy. Right, after putting, so because at that point load is not there, so we have to apply the load. So we applied the load, what? That is PF. Now because of this PF, find. So first C will be equals to what? I equals to 1 to K. This formula already we had seen. 0 to Fi. Right. This all complementary energy 0 to Fi lambda I dFi minus R equals to 1 to N delta R PR. Now what is the next step? Differentiate with respect to this fixed load. So this C will be equals to what? Del C by del PF equals to what? Here. I equals to 1 to K 0 to Fi lambda I dFi by dou PF minus, so here just see, so this is the general equation. So for second point, if you are finding at point C, so deflection at this point will be there, whatever load is acting, According to that, so only this delta R will left, because this PR is already the fixed force. Or in terms of, if you will write, okay, then let me first write at this point. For first C, I'm writing this one. So for this point C, that implies C equals to sigma I equals to 1 to K integral of 0 to Fi lambda I dFi minus R equals to 1 to N delta C and PCF or PFC, fixed load. Right. Now, according to this, what we have to do, we have to remove that fixed load. So differentiate with respect to fixed load, that is PCF. So delta C by delta PCF equals to, here there is nothing, this will get divided, I equals to 1 to K 0 to Fi lambda I dFi by what? Or del Fi by del PCF, right, minus del, this one R equals to 1 to N, right. So this becomes, because now this is not required for that particular point only we are finding. So this PF becomes 1. So simply delta C. Now make delta C as equals to 0. This whole thing equals to 0. So delta C will be equals to this one. Yeah. So for a stationary value of C, delta C by delta PVF equals to this one. Right? So this equals to 0. Now delta C will be equals to I equals to 1 to K lambda I into del Fi by del PF as before. This also we got. If instead of the arbitrary dummy load PF, a unit load were placed at C unit load, right, the load in the ith in linearly elastic member would be just simply Fi equals to delta Fi by delta PF into 1 because of this unit load. So that's why it's named unit load. And generally we can add, put instead of fixed load, we can put the unit load. As a result, the term del Fi by del PF in the above equation equals to the load in the ith member, that particular which member we are finding, caused by a unit load at C, and equation can be written. Same equation can be written as what? I equals to 1 to K. So see here. Lambda I for lambda I and then delta Fi. So lambda I is what? Here. This into this one, right? By AE and then for ith member Fi. So delta C will be equals to lambda just changed. Lambda is this one. Fi into 0 and Fi 1 Li by Ai Ei. So this is the unit load. Means this lambda is what? Fi 0 into Li by Ai Ei. And this is the fixed, that unit load. So F1. So Fi1, okay, where Fi0 is the force in the ith member caused by the actual loading, and Fi1 is the force in the ith member caused by a unit load placed. So this is the actual load, what is acting in that member, and this what we applied instead of fixed load, that unit load method. So unit load, that is here, and the required deflection position and direction. So by this we can find the deflection. Okay, so that is in terms of what? Force. Now we will see in terms of moment. So let's see here. The well-known relationship between bending and rotation and torsion and rotation. Right, bending and rotation and torsion and rotation. The in between that relationship leads to similar expression for deflection due to bending and torsion of linear structure. So how that is related. As a result, for a member with length L and flexural and torsional rigidity. So flexural rigidity is EI. Torsional rigidity is GJ. So delta B because of that moment M. So delta BM is equals to what? Over integral L M naught. M naught is what? Moment in actual, because of actual load, and M1 because of moment because of unit load by EI into DZ. And delta T, that because of torsion is T naught torsion because of the actual load acting, and T1 is the torsion because of unit load by GJ, that torsional rigidity into GZ. So let's see here, where M0 is the bending moment produced by the actual loading, and M1 is the bending moment produced by a unit load applied at the required deflection position and direction. Torsion is the same way. So torsion at T0 is torsion because of actual loading. T1 is torsion because of unit loading what we applied. Okay. This is the way. So either in terms of moment if it is given, then we can use this formula. In terms of torsion it is given, then we can use this formula, or for load we can use this formula by unit load method. So by fixing, instead of fixed load, we can just replace with the unit load. Remaining everything will be same. Okay. So this is what, again, the reference THG Maxon aircraft structure, that is this one, Butterworth Inman Limited 5th edition, or it's not necessary 5th edition. Whatever you are getting, almost the content is same, only they added some extra numericals. So whatever the Maxon book you are getting, you can see the theory and derivations will be there. So you can just refer that one. Okay, and if that you have any problem, you can just come to me, or you can just comment on the video. I will clarify your doubts. Okay. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.